Galilean transformations. Reference frames and relative motion were introduced in the Kinematics 1D unit of this course. These concepts will now be expanded so that calculations can be made to relate the position, velocity, and acceleration of objects in different reference frames. They will also be expanded to motion in 2 dimensions. In order to describe where something is or its motion, you need to relate it to something else. That's the purpose of a reference frame. Choose a coordinate system in space and make measurements relative to the system. There is no one preferred reference frame, and frequently there is a need to translate measurements made in one frame to another. One reference frame can even be moving relative to the other. As long as the frames move with a constant velocity, that's key, zero acceleration, relative to each other, we can use a Galilean transformation. Accelerating reference frames are the province of general relativity and won't be covered in this course. In order to describe where something is or its motion, you need to relate it to something else. That's the purpose of a reference frame. Choose a coordinate system in space and make measurements relative to the system. There is no one preferred reference frame, and frequently there is a need to translate measurements made in one frame to another. One reference frame can even be moving relative to the other. As long as the frames move with a constant velocity, that's key, zero acceleration, relative to each other, we can use a Galilean transformation. Accelerating reference frames are the province of general relativity and won't be covered in this course. Before the math is done, think about different reference frames. If you're sitting in a bus that is going 25 meters per second, which is roughly 56 miles per hour, the person sitting next to you, relative to a reference frame that has you at the origin, is not changing his position, and his speed relative to you is 0 meters per second. If someone is standing at a bus stop, relative to a reference system that has her at the origin, the person in the bus is moving at 25 meters per second and is getting farther away from her. And if a bus is moving parallel to your bus with the same velocity, a person in that bus would agree with you. Your seatmate looks stationary. Who is correct? Why, you all are. Let's start by choosing a 2-dimensional reference frame based on Cartesian coordinates. That's the old XY stuff that hopefully you're familiar with. We'll only be solving problems in 1 dimension though. The stationary frame, over here in black and marked with an S, is not moving. Then choose the M, a moving system, that's in red, over here, and put it in motion with a constant velocity, and we'll call that velocity u, and that is the velocity of the M system with respect to the S system in the x direction. And let's take an event over here. The coordinates of that in the xy system will be x comma y. All right, so we'll draw a little arrow to that. In the x prime system, the system that is moving, the coordinates will be x prime and y prime. So let me delete the marks here and just pause on this and check it out and make sure you follow everybody on this slide. Now let's add a bus and we'll attach that to the M frame, the moving frame, this red frame right here. And we have an observer here at the stationary frame, the stationary system. The bus and the M frame is moving at a speed u with respect to the stationary observer in the S system. The bus is at rest with respect to the M frame. So as the M frame moves, the bus goes with it, and this person over here does not move. U is the relative velocity of the 2 frames. The observers in both frames agree on this velocity, but each will express it in the opposite direction. This is a simpler example, as only one of the reference frames is moving. Okay, we're keeping this frame stationary and moving the M frame. One more thing now. We're going to add a person within the bus. And that person moves at a velocity v sub m relative to the bus, because this person is in the moving frame. The person is also moving at a velocity v sub s with respect to the stationary observer. The Galilean transformations enable the calculation of the position, velocity, and acceleration of the person in both frames, the stationary frame and the moving frame. This only works for inertial reference frames. Both frames need to be inertial. That is, they are moving at constant velocities, zero acceleration. All these motion parameters are vectors. Since we're only working in one direction, vectors to the left will make them negative, and vectors to the right will be positive. And here are the transformations. First, the Galilean position transformation comes from the second kinematics equation, and a is equal to 0, right? Because neither one of these frames has an acceleration. It's going to be x is x prime plus ut. So x is what this person is measuring. X prime is measured by someone in the bus. U is the velocity of the moving reference frame, which in this case is the bus. So x is the position of the bus rider in the stationary frame, just saying it again. X prime is the position of the bus rider in the moving frame. The velocity transformation is v sub s is v sub m plus u. Vs is the velocity of the bus rider in the stationary frame, and Vm is the velocity of the bus rider in the moving frame. And finally, the acceleration transformation, As, whatever the acceleration of this person here in the stationary frame, is exactly equal to the acceleration in the moving frame. Now I know we've been talking about A is equal to 0, right? But that only applies to the reference frames. The person here can have an acceleration, but the frames, the S frame and the M frame, must have 0 acceleration. Let's do a couple examples now. A person, right over here, is walking with the speed of 1.3 meters per second from the front of the bus to the back of the bus, and that's v sub m. The bus is moving at a speed of 22 meters per second. What speed does an observer at a street corner observe for the person in the bus? Let's write out the givens. The person has a speed of 1.3 meters per second, but he's going from the front of the bus to the back of the bus, so that's going to be a negative velocity. So v sub n is minus 1.3 meters per second. U is the velocity of the bus, and the bus is to the right, so that's positive. We use the Galilean transformation for velocity, which is v sub s is equal to v sub m plus u. Use a negative value for v sub m since the person in the bus is moving to the left. We substitute in our givens, and the observer here, the stationary observer, sees the person moving at 20.7 meters per second to the right, which is a bit slower than the bus. Why? Because the person is moving opposite the direction of the bus's motion. Example 2. A person is sitting in a bus moving at a speed of 16 meters per second. The person is sitting in a position of 4.2 meters from the back of the bus. All right, so this distance here, according to the person, is 4.2 meters from the back. The back of the bus passes an observer sitting on a park bench at t equals 0 seconds. After 5 seconds, at what position does the observer see the bus rider? The givens are the speed of the bus, which is u, the position of the person relative to the bus. So the person right here is at 4.2 meters from the back of the bus, and that's in the moving reference system. And time is equal to 5 seconds. Find x, which is the position that this person sees the bus rider at. Use the Galilean transformation for position. X is equal to x prime plus ut. Use a positive value for x prime since the person in the bus is in front of the back of the bus. Here's our equation. X prime, this is the position of the person relative to the moving reference system. Here's the velocity of the reference system m, which is where the bus is tied to. Here's our elapsed time. And we find that after 5 seconds, this person observes the bus rider 84.2 meters away. The bus rider relative to the bus is still at position x prime equals 4.2 meters. For an object in a reference frame m that is moving at a speed of u in the x direction, the Galilean transformations relative to the stationary frame S are, well, here's our position one. X is equal to x prime plus ut, where x is the position of the object in the stationary frame, x prime is the position of the object in the moving frame. Vs is equal to Vm plus u, and As is equal to Am. If an object also has a position in the y direction in the moving frame, one more transformation is added, y is equal to y prime. Observers in both reference frames measure the same y position, velocity, and acceleration of the object. A common problem involves a boat crossing a river. The water is flowing parallel to the riverbanks, and the boat captain intends to sail perpendicular to the banks to land at a spot directly across from the boat's starting point. So what we're looking at is this. We've got the river going this way, and the boat wants to go directly across. The problem will be solved with the information provided in this unit involving the Galilean transformation and vector addition. Example 3, Galilean relativity. Two kids are on a powerboat capable of a maximum speed of 4.2 meters per second and wish to cross a river 1,200 meters to a point directly across from their starting point. The speed of the water in the river is 2.8 meters per second. A. How much time is required for the crossing? Assume the engine is operating at maximum speed. And B. What angle theta relative to the line connecting the 2 points on the riverbanks is required? How much time is required for the crossing? So we write our givens. Here's the speed of the water. Here's the position. And please note here, the position in the fixed reference frame, which is this observer down here on the bank of the river, is the same exact y position as the boat will be in its reference frame. This is the maximum speed of the boat, and we need to find time. The XY frame is fixed to the riverbank. That's the black line over here. The water flow is represented by the moving X prime Y prime frame at speed u. That's in red here. Here's the speed u. Here's the moving frame, which is red, and here's the stationary frame. And here's our boat over here. A person sitting on the riverbank over here at point A will see the boat moving straight across the river to point B. If the boat points directly at point B, let's say it's pointing right like that, the water will push it to the right. It's going to push it this way, and the boat will never get to point B. It'll land somewhere over here on the other riverbank. The boat captain should aim the bow, which is the front of his boat, to the left. So that's in that direction there. In this way, even though the boat is aimed as indicated on the picture, it will actually move in a straight line from A to B as observed by the person on the riverbank at point A. We will start with a vector diagram and show three different velocities which will make a velocity triangle. Over here, the boat is pointing upstream, you would call this. That is the maximum velocity of the boat, Vmax, and that's in the stationary reference frame. We then have the water moving this way. That's the velocity of the water current, and that is our moving rest frame. And finally, we have V sub AR, and that's going to be what? V across the river, and that's the velocity the boat makes across the river as observed by the person on the shore in the stationary reference frame. And we've kind of put all this other stuff here a little lighter so it doesn't get confused with the vector diagram. And over here is theta. We'll be looking for that in part B. Vector addition shows that the vectors Vmax, right over here in the dashed line, plus the vector u in purple, add together to find the velocity V sub AR, right over here. The three velocities make a right triangle, so use the Pythagorean theorem to find V sub AR. So we have the absolute value of Vmax squared equals the absolute value of V sub AR squared plus the absolute value of U squared. We rearrange that to solve for V sub AR, and we take the square root of both sides. We substitute in our values. Here's Vmax, here's U, which is the speed of the water, and we find that V sub AR is 3.13 meters per second. That's this velocity right here, V sub AR. According to the Galilean transformation, the distance in the y direction traveled by the boat in the moving frame is equal to the distance traveled in the stationary frame. So we have delta y prime is equal to delta y. Then the time will also be the same, t prime equals t. So to calculate t, it's delta y over VAR across the river, and we get 383 seconds. The three velocity vectors also make a right triangle because we have the river moving this way, and we're crossing the river this way from riverbank to riverbank, which is perpendicular. So we just use trigonometry. We have theta is the sine inverse of u over v max. We substitute in our numbers again, and the boat captain should be aiming the boat at 42 degrees to the left of the vertical, right down there. A final point for this problem, we have our velocity vector triangle right here that we've used to solve the problem. And then just wanted to show you what the boat's going to look like. The boat is pointing this way, right, at angle theta, which we solved for. It stays pointing that way, but the water pushes the boat to the right. So the observer on the first boat does see the boat move from A to B, but it's at an angle. The boat points to the left as it works against the current, as if it were sliding across the river.